All right, so we're going to kick this off. Welcome everyone to the ColumbusJS. This is the JavaScript user group for the city of Columbus, Ohio. But because it's COVID-19, 20, 21, 22, whatever it takes, we are, of course, virtual like the rest of the world. And so this really isn't ColumbusJS. This is just, I guess, JS. We do talks that are JavaScript and JavaScript adjacent. My name is Guy Roast, and I'm the Guy Roast. My name is Guy Royse, and I am the organizer, president, MC, czar of the JavaScript group here. And I have the distinct pleasure tonight of introducing myself, awkwardly enough, because I'm also the speaker tonight. So you can see up here, we got a slide, Mystery Machine Learning. This is the talk I'm doing tonight. It's a talk on recurrent neural networks with a Scooby-Doo theme. So I'm going to get started here, but before I do, are there any questions amongst anyone before I start? Your stunned silence is very reassuring. So let me get over to I'm the mascot. That's right, Matt. I'm the mascot. It's like, this is all just a big, like a Brutus Buckeye head, really, and I'm actually not a member of ZZ Top. So yeah, welcome everyone. I'm gonna go and get this started. So I sort of introduced myself already. I'm a developer advocate at Redis Labs. And so a lot of my job is running these sorts of things and giving talks and creating content and helping developers learn about and understand the products we have at Redis Labs. Redis Labs is, yes, that Redis, the Redis that everyone says is a cache, but is actually a lot, much more than just a cache. There's a lot more going on with Redis than just caching. That's where I work. And so getting people to know that Redis has more going on. And one of the things that Redis has going on is there's a RedisAI module that extends Redis. And I'm going to talk about that a little bit tonight. But before we do, I'm going to talk a bunch about recurrent neural networks. And this is a data science talk. And so I always like to give the big caveat that before I give a data science talk, which is this one, IANADS. And I always ask everyone, what does this stand for? But I've done it enough now that a lot of people that are here know what it stands for. It stands for, I am not a data scientist. I am not an expert. I'm a fan of data science. I think it's fun. I think it's interesting. And so what I like to do is I learn how a thing works because I'm curious. And then I build a talk and share what I've learned. And so if you're a data scientist, you probably know more about some of these topics than I do, but that's okay. A lot of us are developers. I'm a developer. I've been writing software for a long time. And so getting sort of an intuitive understanding of how things like recurrent neural networks and neural networks in general work is really valuable. Just to understand what this data science stuff is and why I should care. And when I have to work with data scientists and the tools, I can use this knowledge to communicate with them more effectively. And you can even do a little bit of it yourself. Although my advice would be, as a developer, do not pretend that you're a data science and go do data science things, because you will build crappy models, which is what we're about to do tonight. They will be overfit and make the wrong assumptions, and they'll be biased, and the data scientist has a lot of training that you as a developer don't. You can get that training, but it takes years. So you're better off pairing with the data scientist. So I'm not a data scientist. I'm not an expert. I just think this stuff's cool. So in addition to not being a data scientist, I am a lifelong watcher of Scooby-Doo. I've been watching it since before I can remember. It's been something that's just always been a part of my life. Not as much as it used to be. I'm 49 years old, so I'm not, making sure I get my daily dose of Scooby-Doo like I did when I was 7. But it's still something I enjoy, and every now and then I'll go back and watch an old episode just because it's fun. And I can actually I can laugh like Scooby-Doo. So that's my one unique talent in the world, is I can laugh like Scooby-Doo, and I'm regrettably going to do it for you all right here now. So hang on a second. I kind of got to clear my palate to do it. So yeah, so that's all I got. Between that and sounding like Hank Hill, that's the only impersonations I could do. But yeah, so Scooby-Doo, of course, is a beloved show that we've been watching since we were children. And it always was revolved around solving a mystery. And the mystery was always there's some bad guy who's is posing as a monster or some supernatural thing. And the Mystery Inc. comes in and figures out that it's actually just a man in a mask. It was never, the ghost of Saltmarsh or, Redbeard the pirate or any of those guys. It was always just some man in a mask who had some agenda. And so they solve mysteries. And we've got a mystery that we're going to solve tonight, too. We're going to use recurrent neural networks to take lines from Scooby-Doo and lines that you make up and tell you who said them. So we'll give it a line like, what are we going to do now, Scoob? And then it will predict that was said by Shaggy. And if we give it Jeepers, then it'll predict that that's Daphne. And if you say Zoinks, it'll be Velma, et cetera, right? And so we're going to do that with recurrent neural networks. Here's what we're going to build. We're going to actually build an application. And I've got a data set of lines from Scooby-Doo, the movie, and the cartoons, various sources. And it's got all the lines from Mystery Incorporated. So Shaggy, Scooby, Velma, Daphne, and Fred are all in there. And it's just a simple CSV file. It's who said it and what they said. It's the whole data set. We're going to use that data set to build a neural network, a recurrent neural network that can predict who said what. We're going to take that recurrent neural network, we're going to deploy it to RedisAI, and then we're going to build an application that allows us to invoke it. And so we're going to use that model in RedisAI, and we'll be able to type in whatever we want, and then it will tell us who it thinks would have said that if that were a line from the movie. And then we'll know if it's Daphne or Fred or Scoob or Shaggy or Velma. I need to fix the timing on that. It's a little too slow. It doesn't match my speaking rate. But that's the idea. That's what we're going to build. Now, obviously, we got a lot of stuff we're going to cover here. And so we need some help. I'm going to go into neural networks and how they work in a general sense. And we're going to go fairly deep into how they work. We're going to look at individual neurons and a convenient way to think about neural networks. And then we're going to go into recurrent neural networks specifically and show how they're a different type of neural network using the same principles, but configured in a different way. We're going to cover Keras and show how you can use Python code and a domain-specific language around neural networking to build recurrent neural networks and neural networks in general. And then we're going to cover RedisAI, and then we're going to have a big demo where we show it all working. So that's the plan. Sound good? Excellent. And I forgot to mention this at the beginning, but if you have a question at any time, I'm not monitoring Twitch chat. So if you see a question on Twitch chat, just let me know, Matt. But if you have a question, just unmute yourself and ask. We're here in a Zoom. It's all good. Just go ahead and unmute yourself, ask, interrupt me. And that's totally fine. It's a little more fun when it's more interactive. So that's the best way to ask a question. I do have the Zoom chat up as well. So I'll see those come in if you bring them there. So what are neural networks? That's a good question, right? Well, neural network is a series of virtual or artificial neurons that are arranged in layers. And each neuron takes numbers as input and puts numbers out as output and feeds them into the next layer. And so you've got your input layer where you have your input data. Here we have 4 values coming into this neural network, x0 through x3. I did zero base because I'm a programmer and not a data scientist. And so this neural network takes as input 4 numbers. And then you've got hidden layers where the numbers from the input layer are transformed over time, as it goes through the layers, leading to an output layer, which gives us our answers. And what these really do is they take numbers in and they put numbers out. And so you can think of these as a function, right? Like a mathematical function, a function that would draw a line. And so we, for example, maybe this function would draw a line that's shaped like this. And then we can use that line to answer questions. The line in many ways is the model. It's the machine learning model. For example, you could use that line to divide something into two spaces. So you've got things that are above the line, it's in one class, and things below the line are in another class. And so you could classify things. You could say hot dog, not hot dog, right? If it's above the line, Scoob. Below the line, not Scoob. And so this is how you can use these lines that neural networks can draw to classify. You can also use them to do regression, which is you can pick a number on the line. So for example, here we have the ratio of Scooby snacks to the spookiness level of a particular task. So how many Scooby snacks would it take to do a thing that has a spookiness level of 4 or 1? You know, and so the point on the line is what the model predicts. So you're instead of saying what's on what side of it is, you're saying, well, the spookiness level is a 2. How many Scooby snacks? Oh, 2 Scooby snacks. So it predicts a number. So this is a regression problem. And so this is what this neural network does. It makes a function that draws this line. But let's dive down into the individual neurons and look how they work first. And then the whole network will make a little more sense. So this is a simple neuron. This is the simplest neuron you could do. It's got one input, which is X, and it's got one output, which is Y. And right now, this tells you that it's going to draw a line, right? It's going to draw a line on a two-dimensional space. It has a weight. The weight is what's multiplied by the input. It has a bias, which is added to that multiplication. And so to look at the formula, and so these are the 4 values that make up a neuron. Make up might be the wrong expression, but it's the things that we care about. It's the math that's happening. If you're paying attention, our formula ends up looking like this. X times W plus B equals Y. X is the input, W is the weight, B is the bias, and Y is the output. And if you're astute, you might recognize this formula. If you just take that W and turn it upside down and rearrange the arguments, this is Y equals MX plus B, right? And so the weight is the slope of the line that we're going to draw, and the bias is the Y-intercept. And so a neuron, this neuron, draws a straight line. That's what they do. And so it could draw that line. They could be skewed at lots of different angles, right? You could draw lots of different lines. But that's all a neuron really does, is it draws a line. Now, this straight line might not be what you want. You might want a line that is a little less linear. Yeah, sorry, I didn't mean that to be a joke, but I guess it kind of is. And so if you want a less linear line, then you can use an activation function. So an activation function is a function that is called after we've done the math for the output. So if you think of the neuron as a function that draws a line, then inside of it is another function. And so what it does is it takes the value and changes it in some fashion. There's several common activation functions. I'm going to talk about 3 of them really briefly, and there's really only one we ever use. There's a sigmoid. So you can take that number and get a number from 0 to 1, a number that approaches 0, a number that approaches 1, and it will hover there around 1/2. And so you take that number and you run it through here, and it squashes all these numbers out. And that works okay. That's a way you can transform your output to make it a little less linear. It makes big numbers not have as much of an impact on the model as smaller numbers. But sometimes you want the bigger numbers to have an impact. And so sigmoid doesn't always work. You can do a hyperbolic tangent, which is basically a tall sigmoid. It goes from -1 to +1 instead of from 0 to 1. But it approaches 1, it approaches -1. It never reaches that value. But instead of having a median or a middle point of 1/2, it has a middle point of 0. And so this is sometimes used as well. I have actually never had a reason to use either of these. I almost invariably use rectified linear units, or RELU. And RELU is a very fancifully named thing that's actually really easy to understand, which is max x comma 0. If it's 0 or more, it's what it is. Otherwise, it's 0. So all your negative numbers become 0. That's all it is. I mean, looking at this graph here, it becomes really self-evident, right? All these negative numbers are 0, and these are just what they are. And this is turns out to be one of the better activation functions used with neural networks. I think negative numbers kind of make things get a little wonky. Like once you flip down to the negative numbers, you're training these things and the weights are going up and the biases are changing, and then you adjust them such a way and then bam, all of a sudden it goes negative, and then all these things that weren't important are important in a really different way. I think that's why RELU works, but I'm not a statistician. I'm not a mathematics person. I'm a developer. And so this is just sort of my intuition about it. But that's what RELU does. We're going to use RELU in our examples. And so that's what a neuron does. Now here's a beefed up neuron. It's got 3 inputs instead of just 1. And it's got 1 output. And so, I said that we're drawing lines to separate space. And if it's on one side of the line, it's this class. If it's on the other side of the line, it's in this class. But that's actually not what we're doing. We're doing that, but we're doing it in multiple dimensions. So here we have 3 variables coming in. So it's like, that is a space. That's a 3-dimensional space. And Y is our output. So we have a 4-dimensional space being bisected by a 3-dimensional space. So what we have is a hyperspace being bisected by a hyperplane. So the hyperplane always being dimensions minus 1. So if we got a 10-dimensional space that, because we have 9 input variables and 1 output variable, then the 9 input variables define the plane, the hyperplane, and then the 1 output variable gives us that extra dimension for that. RELU is Scooby Snacks, yeah. Yeah, exactly like Gandhi becoming terrified when he has access to nuclear weapons. It goes around the horn, right? But so it's the same idea, but we're doing it in multiple dimensions. And so it's not really a line and a plane, it's a hyperplane and hyperspace. So, but it's exactly the same, almost like exactly the same math, and it looks like this instead. So instead of just multiplying, we sum all the multiplications. So it's the sum of the inputs times the weights plus the bias, which expressed with sigma notation is this, which just means for all the values of I, do this thing and add them together. And this is the heaviest math we're going to get into in this entire talk. So I used a Greek letter, and now I feel smart. Yeah. So, and that's pretty much neural networks in a nutshell. So you end up with this network that is a function made up of functions that have activation functions inside of them. And what it means is instead of drawing a straight line, you can get all kinds of interesting curved lines. So you can draw a really complex line with a neural network. You can draw a circle. You could draw lines that have pockets in them. Which could be really useful for machine learning. And so you end up with something like, who said that? And you get different locations where you can find out whether it's a Daphne, Fred, or Velma here. So any questions on neural networks so far? Cool. Yeah, it looks really scary. You're right, Matt. It looks really scary for something that's basically 4H multiplied by weight, then add the bias. That's all we're doing. That is literally all we're doing. So what about recurrent neural networks? Well, what makes them special? Well, in some ways, they're not special. They're made of neurons in the same way that a regular neural network is, but they have multiple input layers. And so that's represented here by X0, X1, and X2. And it has multiple possible output layers. And then it's got these hidden layers in the middle. And these hidden layers are just the same neurons, just like we were looking at in our previous neural network. It's that same hidden layer of neurons. only this is one's wired up a little bit different. The input layers, the circles that are input layers, they're actually arrays as well. So they could represent multiple items. They don't have to be, they could be a single item. But their input layers, just like the last one, they could have like 3 or 10 or 100 or 1,000 values in them. But what recurrent neural networks do is they arrange data chronologically. So they're good with time series data, data that has a sequence and where the sequence means something. So the way they work is that the input layer here is evaluated and run through this hidden layer and gives us an output. And that output can be shunted up to an output layer, can also be put into the next hidden layer. And then the next hidden layer has the next input. So this could be like all the temperatures in the state of Ohio yesterday, or 2 days ago. These could be all the temperatures in the state of Ohio the day before that, or yesterday, and these could be all the ones for today. And so this is time series chronological data. And when you're trying to predict something in a sequence, knowing what happened in the past matters. If I say 1, 2, 3, what's the next thing I'm going to say? 4, right? If I say 12, what's the next thing I'm going to say? Well, who knows, right? I could go to 11. I could be counting down. I could go to 13. I could be counting up. I could be counting in grosses or dozens. And so I could say 24 and 36. You have no idea. You don't have the sequence to tell you that. So the sequential data matters. And so when we come to this second hidden layer, we take the next data in the sequence and the previous conclusion that was drawn from the previous data that was entered to make our next conclusion. And then that conclusion feeds into the next layer, and you get the next level of input. And so it gives the neural network a sort of memory where it can remember things that happened in the past. And then this process continues, and then eventually you get some outputs. This particular one has multiple inputs and multiple outputs. There's lots of ways we can configure these things. But you can take sequential data and turn it into other sequential data, or you can take sequential data and turn it into a single point of data, or you can actually take a single point of data and turn it into sequential data with recurrent neural networks. I'll show you what I mean here in a moment. So here we have a many-to-many neural network. This is one we've been looking at. These are good for things like translation and chatbots. So you think about a chatbot and what a chatbot does and what a translation software does isn't really that different. It's just knowing different things. And so if you're doing translation, you put in words in English and they spit them out in Spanish. And if you're asking a question, you're getting an answer. But from a neural network point of view, they're not really that different. So here we, for example, put in the words, "Look out, Scoob." And so we're building a Scoob bot that responds, as Scooby would, to prompts. And then the Scoob bot would respond with "Roke Raggy." And so that's how you would use it for a chatbot. So it's taking that sequence of words. I said 3 words that gives it meaning. Think about it, right? If you used the cat ate the dog, that means one thing. If you say the dog ate the cat, that means another thing. And so that sequence matters in translating in chatbots. And so that's how you do it with many-to-many. You do one-to-many. One-to-many is the best example I can think of for this is image captioning. So if you give it an image, it can tell you what's in it. So if you give it like usually that'd be paired with like a convolutional neural network of some sort. But so here we give it an image of Daphne and it generates something that Daphne might say. Like Jeepers, they mean business. And you've got many-to-one, which is the one we're going to play with tonight. Many-to-one can be used for text classification. So, which is what we're going to do. We're going to say, who said this? Which person, which class does it belong in? Is this Shaggy, Scooby, Daphne, Fred, or Velma? They can be used for sentiment analysis. Give it a sentence and it can say, give you a single value saying whether this is, from 0 to 1 representing 0, this is really negative, to 1, this is really positive. You could use it for predictive text. I've put in these words. What's the next most likely word I'm going to say? And so, this is, your iPhone is doing this. And so here we've got, hey, let's split up. Who says that? Fred says that. So this is classifying text. So this is what we're going to look at in detail. Here we've got a classic line from Velma. I can't see without my glasses. And we made this one a little bit bigger. We've got 7 elements in it. 1, 2, 3, 4, 5, 6, 7. My real one is a lot bigger than this. But here we've got, I can't see without my glasses. Velma was supposed to come in and be animated. I messed that up. I got to fix my slide. But we can take this text, run it through the neural network, and it would tell us Velma. Except neural networks don't operate on text. They operate on numbers, right? I mean, it takes floating point numbers, runs them through a function, where, draws the line, runs it through the activation function. This is still happening here. And so we need some way to turn our words into numbers so that we can actually do things with them. And that process is called tokenizing. And so what we do is we take a corpus of text. And here, in this scenario, we've got our data sets of lines from Scooby-Doo. There happens to be 24 words in here exactly. And we just count them. And that's it. We count the words. And then we create a little lookup table that says this word is this number, and this word is this number, and this word is this number. And the more frequent words go to the top of the list, and the less frequent words go to the bottom of the list. So the word like is like in here 3 times, man. Whereas the word zoinks is only in there once. And then I went ahead and sorted them alphabetically too, because I'm anal retentive. But that's what's going on here. It's a substitution cipher. It's like A is 1, B is 2, C is 3. It's, that little code you do when you're a kid. We're just doing it with words. And so we're saying this word, Jeepers, is now 12. So, and if you're astute, you might have noticed that it's not 0-based. It's 1-based. And there's a reason for that. And I'll touch on that in a minute. But if I'm a developer, I would want it to be 0-based, right? But in this case, it's not, and there's a reason. So yeah, so here we encode this. So if I take the phrase, I can't see without my glasses, that encodes to 10, 8, 21, 23, 4, 3. And if we look at any of those numbers up like 21, you look it up on the table and it's C, right? We've tokenized and encoded this sentence. So you might have noticed there wasn't a word in in place number 1 here. You also might have noticed that it's right justified. Those are both for a reason. The place it was blank is actually null, right? And we don't have a lookup value for null because null is 0. So if we run into a word we haven't seen before, we give it the value of 0. That's why we did it at 1-based. So it's null, I can't see without my glasses. And so because the neural network has to receive 7 inputs because that's how many it has. You got to provide something for it. And that's the word that you would use. You would use a 0 for that. So the next thing we do is we take all these words and we do what's called one-hot encoding. So this 0, 10, 8, 21, 23, 4, 3 thing on the left is I can't see without my glasses. And to one-hot encode each of these values and have that be that one-hot encoded thing to be input into the network instead, what we do is we take an array that is the width of our entire dictionary. So we got 24 words in our corpus, and so it's 24 words wide. Corpuses of text are going to probably be bigger than that, like maybe 10,000. And so you can see that this is really wide. And all we do is position 1 in there is a word like Reggie, glasses, my, right, Scoob. They're all each one of these words. And we just put a 1 in the column that corresponds to that word. And the rest of them remain 0. So the value that's hot gets the 1 in it. And the rest are 0. So it's 1 hot, right? The hot column gets the 1 to encode these words. And so the number 10 goes to I, the number 21 goes to C, et cetera, et cetera. And so this, needless to say, creates a lot of data, but it's what you want when you have classes. This is how you store class data, discrete values in a lot of machine learning algorithms. But that's a little big. And so what we'll do is we'll do a thing called word embedding. What word embedding does is it takes each of these words that we entered and sort of compresses them down to a tighter row of numbers. And so the number glasses, this array here, right here, this one hot encoded array that has the number glasses in it, and the rest of them are 0, is going to correspond to a row in the embedding table. And then that value will be used instead. So if we look here, 1 is in the column for glasses, and then we got these numbers. So these numbers are what's actually going to be put into the neural network. The values in here are trained when we build our network, and I don't really know how it works. I just call model.fit, and I know that it does. But the idea here is that words that are more closely related in meaning have larger numbers. And so these columns sort of represent sort of a semantic context. And so like if we had the word spectacles instead of glasses in our example, or in addition to, spectacle and glasses would both have large values in column 5 here, because they're a related concept. Whereas like, and goggles might also as well, whereas apple has nothing to do with glasses. And so it would have a larger number in another column, maybe the same column that had orange, because they're both fruits. And so it's sort of embedding the meaning of the words, the semantics of the words. And my guess is that this is handled with a large dictionary of English words. But I actually really don't know. I haven't dug into how that works. I just know how to make the code work to do it. And I understand what it's accomplishing. So we're not actually putting, when it's all said and done, we've gone through this process, we're not actually putting in these words, we're putting in these numbers. Null returned all zeros, so it's a bunch of zeros. I can't see without my glasses, and these are the word embeddings for each of those words. So that's actually what's coming into the recurrent neural network. What's really being output is not a picture of Velma. It is instead a picture of Velma, right? It is actually 5 numbers. And these 5 numbers should add up to 1. And so they're percentages. And each of the positions corresponds to a member of Mystery Incorporated. They're one of the classes that we have. And so we can look at this and say, 83% likely it's Velma, 3% that that's Shaggy, 11% that's Scoob. And so we're putting in these embedded numbers into it. It's running and doing all the processing, all the y equals plus y, all the weights times the biases, weights plus the biases times the inputs, and all that stuff that we talked about earlier, goes through all these layers, and then it spits out one number. Now, one thing that confuses me sometimes with this is that I was thinking of this chronologically, but it's not chronological, right? It's not we put a value in here, and then we run it through here, and then we shove it in here, and then we do this computation next, and then we do this computation next. We're putting it all in at the same time, and it's all, it's like recalculating like a spreadsheet, right? It's like it's a God's eye view of time, right? That's kind of how I like to think of it. And that's one of the things that always trips me up when I'm looking at like convolutional neural networks. They have sort of a natural time thing to them as well, where it's like you look here and you look here and you look here, but actually it's just even wired up in a different way, and it's all happening simultaneously.
Hey, Guy, I got a question for you.
Sure.
Those numbers at the top, are those guaranteed to equal 1 if you total them all together, and if so, how?
That's a great question, and I actually was going to talk about it later, but I'm happy to answer it now. So one of the activation functions you can use is called softmax. And so what softmax will do is on your output layer, it will say, you've got 5 outputs, 1 for each class. Make sure they all add up to 1. So it just adds them and divides. So softmax is, obviously that's a really easy computation. Take all my outputs, add them all together, divide by, divide my current one by that total. So that's how it does that. You don't actually have to do that. You can just take the largest score, but understanding the ratio is often really useful. I think it's more useful than having the raw numbers.
So I have a question. Did we
Yeah.
skip the step where you train this neural network?
So I haven't talked about how the training works. Mostly because
I imagine to start with, it doesn't know anything about Scooby-Doo unless it's already sat and watched like reruns for like, you know, a week or something.
Yeah, I haven't talked about how we train these yet. So the way you train a neural network is you call model.fit. And I'm being a little bit smart there, but at a certain level, that's kind of all I do. It uses a process called backpropagation, and it goes through and figures out what the weights and the biases should be. And it's using differential calculus to do that. There's different functions that you can, optimizers you use to compute those numbers. I don't know enough calculus to know actually how that works in detail, but in essence figures out which value was to blame for, in the neural network for the wrong output, and then we'll adjust the weights of those neurons in those neurons. And it uses stochastic gradient descent to do that, which are words that I've learned how to parrot, but don't fully understand what they mean. I mean, I've looked at some, I just don't have the calculus background. Stochastic means random. Gradient is, it's bigger on one side than the other, and it fades just like a gradient, like, well, here, I'm going to talk about the vanishing gradient problem. It's the numbers get smaller as you go in a direction or bigger as you go in a direction, just like, smearing colors. And descent is, you're actually trying to find this bottom point in this mathematical trough, which is the sweet spot that gives you the value you want. And so it's doing that, but I don't understand how it works. I've seen all the pieces and I have a loose conception of them. But this gradient here, I do understand. It's actually pretty intuitive once you look at it. And this is that things at the end are more important than things at the beginning, which isn't true in language, but is true as far as recurrent neural networks are concerned. If you look at how these work, and you look at the far right here, it takes the word glasses, and it takes the output of the previous layer. They both count equally. And so half of this is glasses. And so I can say, I can't see without my glasses, Scoob, and it's going to say it's Shaggy. Because Shaggy always ends things with Scoob, right? And then the same thing for my, half of the output of this layer here is my, and half of it is everything in the past. And this is why we write justify everything. Because if we left justify everything, the most important thing is going to be null, which means it's going to be wrong. And this is what we do when we train it as well. So this is called the vanishing gradient problem. And for small data sets, it's not a huge problem, but for big data sets, for long sentences, right, it doesn't work. And so there's a solution to that problem, which I'm not going to go into, but it's a good homework assignment, is the long short-term memory and the GRU, the gated recurrent unit. These are alternate ways of doing variations of recurrent neural networks that basically give a little bit of short-term memory to these things so that they can hang on to things that might be relevant and help address that problem. So check those out if you've got time.
Guy, Neil asked in chat, what cost function do you use? Squared differences, question mark?
I'm using, I think I'm using the, I need to look at my code. I have some sample code here. The loss function is a categorical cross entropy, and the optimizer I'm using is Atom. So, because I'm doing, partly because whenever I do classifications, categorical cross entropy has given me the best results. Not so much that I understand exactly what it's doing. Atom similarly so tends to give me, it's a variation of stochastic gradient descent, but I don't really know how it works internally. I'm using sort of the plug and play developer approach, which is put this in here and see if it works, and then put this in here and see if it works and compare, which is why you should work with the data scientists if you're doing data science, because they're going to know why those might be a bad idea. So let's talk about Keras. So Keras is this DSL that I mentioned for making writing neural networks easy. It's written, it's all for Python developers, and it's part of TensorFlow now. It wasn't originally. I did a talk a couple of years back called Deep Learning Like a Viking that I used Keras with, and I used an earlier version of Keras before it was part of TensorFlow. Now it's part of TensorFlow. And so here is some Keras code written in Python. And so this is just a simple, fully connected feed-forward neural network. And so the first thing you do is you create a new model. And this is going to set up your model to be trained. And you're going to say, I want this model to be composed of, here's my layers for this neural network. I want a layer of 5 neurons, a dense layer, meaning a fully connected layer. And its activation function shall be RELU. And the input to that layer shall be 4 posted values. So these are just 4 numbers, whatever they are. So that defines our first 2 layers. Our input layer doesn't really have any, it doesn't have any activation happening. It's just set to the numbers. And those feed into the next layer. Then we define our next layer in the model. And here we don't have to give it an input shape because it's not, doesn't have an input layer. The one above it does. It's just next in the list. And its activation is also RELU, and it's also got 5 nodes. And then our output layer has got 3 nodes. So this is going to classify it into 3 categories probably. And we're using softmax as our activation function, which makes it equal to 1. So we're going to be classifying 3 things, and we can, excuse me, and expect to treat those as percentages. Once we've added all our layers, we call model.compile, and we give it an optimizer, which is the thing that goes through and figures out how to adjust the weights and biases. We give it a loss function, which is the thing that tells us how wrong we were, so that the optimizer can figure out what to fix. And then we got just some metrics for us humans of accuracy, just to look at, because it's convenient for us to say, is this actually accurate or not? So now we have a compiled model. Now to train that model so that we can make predictions, we call fit. And we pass in xtrain. The xtrain is not the train that the X-Men take to get out of, I'm sorry, that was a bad joke. I apologize for that. It just popped in my head and it was a terrible, terrible idea. But no, it's the training data. It's the training input data, right? It's all the features. Y-train are the labels. It's the answers, right? So the X is all the things we're going to provide to it to get an answer. Y contains the answer. And so we give it this training data. We tell it the batch size we want it to work in, and we tell it the number of epochs. So the batch size is, when we first start training this, we're going to set all the weights and balances to random values. Now Keras is going to do that. TensorFlow is going to do that. That's going to happen. By calling fit, that happens. The batch size says, take those random values, run it, do 20, and then use the loss function to figure out how bad those 20 were. Use the optimizer to figure out whose fault it is, adjust. Do another batch of 20. Do another batch of 20. So go through your data in chunks of 20. And then the epoch says how many times you're going to go through your data set. So we're going to go through our data set 10 times. Once we've done that, we can evaluate our model, giving it some test data. So this train data that we used, we presumably had a larger set of data, and we took 80% of it to train it, and we kept 20% to evaluate it afterwards so that our model doesn't become overfit. And so we can evaluate it and get an idea of how well it did. And you're going to see that I've built a model in the demo that is horribly, horribly overfit. And then now we can actually make a prediction. We say model.predict and pass in a value for X, or about values for X. And then it will tell us Scoob, not Scoob. An RNN is pretty similar, but here we can add the embedding layer. And so Keras just knows what embeddings are. So you give it an embedding layer, you say that embedding has this input dimension of my max vocabulary. If I got 10,000 words in my vocabulary, that goes there. The output dimension of the embedding layer is going to be how many columns that we want in that embedding. So we took those 24 words that were in our sample data set earlier. We compressed them down into 6 columns. That's the columns in that embedding layer. And then the input length is how big of a sentence we can handle. So in our case, we're using 7 word sentences as our maximum input. And I picked 7 because it fit on the screen more than anything. So, and so that defines our embedding layer. And then we're going to tell it to build a simple RNN. And we want a number of units in the RNN equal to our embedding columns. Then we add a dense output layer, 5 outputs with softmax. That'd be 5, 1 for each member of Mystery Inc. And now we've got a simple RNN defined that can classify Scoob and the gang. So let's see this actually work. So let me bring up the appropriate terminal. So am I in the right folder here? You all can see my screen. Is it big enough? I know it's big enough for Neil. He's got a massive TV he's watching on, so we're good.
Little bit blurry on Twitch.
Is it? Okay. Let me embiggen it there. That should help a bit. So I'm going to go ahead and get my Python environment set up. So we're going to say source, then build activate. Now we've got a Python environment set up. I have got a build model right here. We're looking at it. And so, no, that's JavaScript code. There we go. There's our model builder. So here I'm bringing in Pandas, and I like to call it NumPy. I know it's NumPy, but I like to call it NumPy. I'm bringing in Onyx, TensorFlow, and Keras to Onyx. And that's for a little bit later. But as we go through here, we've got our training data, which is our Scooby-Doo lines.csv, and we got some file paths here. So we load up our data using Pandas, and then we break out apart the features and the labels. So the features are all the words that they're saying. The labels are who said it. So this is the line. This is the character that said it. And then we want to take those character names and turn them into encoding. So we're going to one-hot encode them. So we create a label encoder using scikit-learn. We give it all the labels, and it will spit out an encoder that will look like this. Basically, it gives us an array of these and assigns them numbers. Puts them in alphabetical order. So that's our classes. And we're going to hang on to that encoder for later, because we can, once we've trained that encoder, once we've called fit on it, we can give it one of these strings and it will spit us a number. We can give it one of the numbers and it'll spit us the string. So it knows that 0 is Daphne and that 1 is Fred and that 5 is Velma, or 4 is Velma. So then once I've got that encoder, I transform my labels, giving me new labels that are now numbers instead of words. And then I want to take those numbers and one-hot encode them. And so I call toCategorical, which is imported somewhere up here. That's imported from TensorFlow. So that creates one-hot encoded names. And so now instead of 4 being Velma, it's 00001. Now we're going to take the words and we're going to use text processing at Keras to tokenize and pad sequences here. So we take the tokenizer and give it the number of words we want it to be the maximum number of words, which is going to be max vocabulary. We're going to fit that tokenizer on a bunch of text. This would be all the lines from the movie. And then we're going to take all those lines, now that we've built a tokenizer, and we're going to actually tokenize them and convert them to sequences of numbers. And so this is a staggered array. So Rut-Row Raggy is I got a width of 3. I can't see without my glasses, has a width of 6 up to whatever our max line length is, up to 150. And so then we got to pad sequences to put zeros to the left of those. So we have empty words to the left. Now we've got a bunch of even shaped arrays. of all the lines. And this little tokenizer has a word index, which we save out to a file, and it looks like this. So there's the, you, to, AI. Needless to say, those are common words. We go down a bit. We find like it's, and it looks like it's got the apostrophe S with the Unicode one. Look, I'm 225. We go all the way down to the bottom. We can see that eyeballs is in position number 2172. So we got a little over 2,000 words in our corpus. So then we can, here we split that data, our X's and our Y's, into 80-20 test train split. And this is the same code that we just saw on the slides. We got embedding matrix columns of 32. So we got 32 columns there. We're building a sequential model. I went ahead and gave it a name just because that's nice. Here's our embedding thing. This is exactly the same code that was in the slide. We add our simple RNN. We got our activation. I actually go off the length of the classes, which is going to be 5. And we compile it, atom, categorical cross entropy, accuracy. We print a summary. We call fit, and we evaluate. And then here we are making some predictions. So I take these lines and I have to go through the same process to encode these. And so I use the word vector and stuff like that. And this is kind of interesting code, but I think I'm going to skip it for now because I'm running a little long. And let's just go ahead and run it. Because the last thing I do is I convert this to an ONNX model and save it, which we're going to use with RedisAI. And I also will save it as a TensorFlow model and use it with RedisAI. And that's a little more involved. The ONNX model is simply a matter of calling Keras to ONNX and calling convert, and then saving it to disk. And that's it. So it's like 2 lines of code. It's very easy to use ONNX. TensorFlow was a little bit more of a hassle with RedisAI. So let's go ahead and run this though. We'll say Python build model. There we go. And give it a moment here to think. I promise this works. I tested it right before. Here we go. You see it's tearing through the epochs. Accuracy is getting higher and higher and higher. This is great. This module is going to be amazing. And then it comes out with a number 11 here with our evaluation. And our loss went from 0.25 to 1.75. Our accuracy went from 95% down to less than 40%. Ruh-roh, raggy. This model is overfit. It is a crappy model, but it works for the lines that I want to use. So if I say Jinkies, it says it was likely said by Velma Dinkley. Here is Jinkies encoded for input into the model. It's an array of word vectors here. 153 is Jinkies. Here's our percentages from the softmax. And so we see that Velma came up at like almost 70%. Like Hang On Scoob gave a Shaggy a 91% certainty. So it's working okay for their catchphrases, which quite honestly is good enough for the talk. Oh yeah, that's a good point, Matthew. The GPU probably I probably was using GPU. But yeah, so that's the model working. So that's an RNN in action. Let's go back to slides and see what's next. So we're going to talk about RedisAI briefly. RedisAI is a module that extends Redis with AI features. And those features are basically so that it can host models and then you can make predictions against them. So instead of running this inside of TensorFlow or running this inside of Keras and using a bunch of Python code, you can deploy your model to Redis and then call it from anything that can talk to Redis, which is everything. And we're going to use JavaScript. And of course, with RedisAI, you get fast interfaces, inferences, and easy integration because everything can talk to Redis, and Redis is known for being fast. It supports multiple backends, which I think is actually its coolest feature. I can take a TensorFlow model, I can take a PyTorch model, I can take an ONNX model, I can put them all on RedisAI. And as long as my input tensors look the same, then my client code is none the wiser. And so this means in this case, actually, I'm going to deploy the same model in Onyx and TensorFlow, and we can call it from the same JavaScript client that I write. This gives you like architecture. This gives you a layer of abstraction between your data science world and your developer world. It keeps the developers from having to use Python unless they want to, while at the same time it gets the developers, gives the data scientists the freedom to pick and choose their platforms as well without breaking a bunch of software. RedisAI introduces two new data types, the tensor and the model. A tensor are the multi-dimensional arrays that are inputs to the models and the outputs of the models. The model is, well, the thing that does the predicting. And so it's pretty easy to use. You can use it from the Redis command line. You load a model into Redis using the ai.modelSet command. You load a tensor using the ai.tensorSet command. These are very inspired names. Then you run the model with model run. So ai.model run. It will then take the tensor that you gave it as an argument, make predictions, and then write them out to a new tensor. Then you can just go use ai.tensorGet and read that tensor. And boom, you've got your answer. So obviously you set your model once, and then you write a tensor, run the model, read the tensor repeatedly. The commands are fairly straightforward. ai.tensorSet takes the key that you want to put the tensor into. This is just like setting a string in Redis. You give it the type that the tensor contains. So this one contains floats. This can be all the, float, ints, all the things we care about. We give it a shape. So this is a two-dimensional tensor. It's, I guess, two tall and 7 wide, or 2 wide and 7 tall. It's 2 by 7. And then we can specify the values that go into that tensor. And these values are the word embeddings. So this is, I can't see without my glasses. Actually, not the word embeddings. These values are the encoded words. So glasses is 3, my is 4, right? Zoinks, like look out Scoob. So 6 is Scoob here. And so we're putting these values for the words into our tensor. So I guess 2 is the height and 7 is the width. That would be the way to think of it. If we want to get that tensor out, we say ai.tensorGet. We can pass in the key that we want to get. We pass in that we want it to return values. You can also return a blob, which will return a binary representation, a protobuf version of it. And we can return the metadata as well, which will tell you the shape and the data type of the tensor. So that's pretty much all there is for tensors. You can set them, you can get them, they have values. Right? You can use blobs, you can use the values. To work with a model, you need to load a model in. You can call ai.modelSet and actually pass the model in as a blob in the command line, but then you're typing binary instructions to Redis, which is a bad idea. And so I always use the Redis CLI-X, and that will say, take whatever is piped in from standard in and have that be the rest of your Redis command. And so you can say model set, give it a key to put the model in, say, this is an Onyx model, this is a TensorFlow model, this is a Torch model. This model is going to run on the CPU, not the GPU. You can pick. And then here is the actual model file written out the disk. And so it'll just read that in, shove it into that field. AI.model run, you pass it the key that contains the model that we just set. And then the input tensor or tensors, you can put multiple input tensors and you can have multiple output tensors. And then this will tell us that Daphne or that Velma said the first line and Shaggy said the second line. So this is the commands to work with RedisAI. Putting it all together, the thing that we're going to build is a little application where we type in rokay that gets sent to Redis. Redis sends that off to RedisAI, which delegates that to the model. The model makes an inference, it makes a prediction, it decides who it thinks said it. That value comes back through those layers and tells us that it is indeed Scoob. So it's time for the next demo, and then we'll be wrapping up. So Come on. That's not what I wanted to do. That's not what you're supposed to be doing. There we go. So you notice at the end, I saved off these models as they're actually here in the model folder, an Onyx model and a protobuf file. I'm going to I've got some JavaScript code which will load those in and then run a server that's we can hit to make predictions. And I wrote a little JavaScript client that takes care of that. So this guy is using all those commands that I was just showing you using a library called IO-Redis. So lots of things here, but these are just constants. The key thing here is that we're going to connect to Redis. We're going to load our 2 blobs from the file system using just FS. Then we're going to call AI.ModelSet. We're going to pass in, we got a constant for the key. We got a constant for the backend. We got a constant for the device, which is CPU. This is Onyx. This is mystery : Onyx. We got the value that we read from the blob, which is a buffer. And then we'll do the same thing for the TensorFlow model. It takes a few extra arguments. It needs the input names, which are defined somewhere up here. Here they are. It needs a couple extra bits of data, so we provide those for it. And then remember that the classes.json and the word index.json we saved off? Well, we need those, so we load them in so that we can encode and decode our words from Scoob. And then we just use express to handle the request, a simple request. We pass in the backend and the line. Those are the 2 arguments we pass in. Throw an error if our backend is invalid. And then this is actually my favorite little bit of code here. I love writing JavaScript like this because we take the words of whatever we sent, the line. First thing we do is we lowercase it, which returns a new line. And then we use a regex to replace, to remove all the letters, only things that aren't letters and numbers, replace them with space. So this strips everything that's not a letter or a number. So no punctuation, nothing like that. Then we replace white space with a single space. So if we have like extra spaces between words and stuff like that, so anything that's 1 or more white spaces, we globally replace that with a single white space. Then we trim off any white space on the edges just in case. We split it on our single space, and now we have an array of words. We use map to map those words using our word index, which is that guy right here. So if the word parents is in there, it returns the number 216. Then because that's going to give us undefined sometimes, we go through and say if it's undefined, make it 0. So it's tearing through these words in a very fun JavaScripty kind of way, very functional JavaScript kind of way, which I like. And then we do the padding to fill it up with more zeros on the left. And then ultimately we set our tensor here, and we call AI.ModelRun if it's Onyx, and we call AI.ModelRun if it's TensorFlow, and then we read our output tensor. And then we transform that and spit out the results. So let's run this thing. So we can say npm start, and that will run the server.js. Oops. That's not going to work because I don't have Redis running. This would be the time when Redis decides to pull my little script decides to pull the latest Docker image, wouldn't it? Okay, so here we've built our model already, so we don't need to do that. So we can do npm start. And so it's doing all the things. It set up the models. It's listening on port 3000. If we go to port 3000, we can give it a line like that. And it's not Jinkies, is it? What's the URL it's listening on? It is listening on slice Jinkies. Maybe it's a post. Yeah, it's a post, not a get. That's why it's not working. So I'd have to spin up Postman. I'm not going to bother with that. Instead, I'm going to run my little client and Python. I know source bin activate. And then I'm going to say, I've got a little web client in here. And I can do this. If you aren't familiar, there's a wonderful trick in Python where you can type python-m http.server for Python 3. And I spelled HTTP wrong. But that runs a little web server from this directory. So it's super easy, a little demo web server. So that's how I always do it for my demos. So if I go to localhost 8000, we can see that I got a little app. Sorry, I heard a weird noise in my office. It's like a clicking sound. I don't know what it is. I'm sure it's fine. My house isn't going to blow up. So let's test this thing out. What's a good line for us to for Scooby to say? It's definitely the predator. If it bleeds, we could kill it. We say look out, Scoob. And I'm going to select Onyx, and it predicts that was Shaggy correctly, right? If I say Jeepers, they mean business. And we'll use TensorFlow this time. It predicts that as Daphne. When I say something that confuses it, like I can't see without my glasses, Scoob, it's going to assume that that's Shaggy. And that's because of the vanishing gradient problem. Scoob is way more important than glasses. I also spelled glasses wrong. Let's fix that. There we go. And so it's not as smart. It's just that the vanishing gradient problem does this.
How about,
yeah.
I won this election by a lot.
It'll probably say
today.
That's clearly Shaggy. Shaggy Rogers for president. What I like to do is I like to put in words that it would have, there's no chance that it would be in the data set, and see what it does. And so they say, like, I can't see without my glasses, SpongeBob. Right. Pretty sure SpongeBob is not mentioned in the Scooby-Doo movie. And it figures out that might be Shaggy. That's actually not a good guess on its part. Let me take the like out and see if it makes a difference. And that's guessing Fred now. But it's able to make a guess.
Doug has a suggestion in chat.
Yes, a confidence number might be nice. In fact, I do that. If we go back and look at the command line that's running here, pay no attention to that. I don't know what that is. In Node, I do spit that out for all of them. So on that last line, it's only 53% confident that that's Fred. For the previous one, which I don't was 55% certain that was Shaggy. So the confidence scores aren't as high. This one here, it was a little iffy on. This one here, it was very certain that was Shaggy. Reasonably certain that was Daphne. Very certain that was Shaggy again. So my little demo app doesn't do that, but I do in fact return these. So, so fun little ridiculous app. I thought it was kind of fun. So it's a little sample code if you want to play with these things. It's all out there on GitHub. We've covered a lot in this talk, so you should have yourself a Scooby snack. That's a fact. Yeah. We covered neural networks, recurrent neural networks, Keras, and RedisAI. Here's all the links. If you want to go play with this stuff, redisai.io is the website to go to for all the things RedisAI. Like it takes you to like the docs. It's the docs. I'm using a Docker image for that as well. I find that's the easiest way to get RedisAI up and running. And if you look at my repo for this code base, you'll see that I'm using RedisAI. I've got a shell script that is used to start up Redis. You can totally steal that. It just pulls the Docker image and then runs it with all the flags it needs to do the things it needs to do. But yeah, and you don't need to memorize these links because I have a QR code at the end. Check us out on some of Redis stuff out. We got a Discord server. I need to update this URL. We're actually at discord.gg/Redis now, which is way cooler. We got our server verified. So, and by we, I mean I got the server verified. So I'm really happy to announce that. So discord.gg/Redis. I'm always on there. So if you have a Redis question, you can hit me up. Redis University has a bunch of free online classes on Redis, although not RedisAI yet. RedisAI is still a lot newer than some of the other things. And we have a bunch of Redis University videos. I've got 3 videos on RedisAI up there as well. So go and check that stuff out. It helps the cause. Code and slides can be found on GitHub. At that URL. The QR code does totally take you there. It is not going to give you up or let you down and take you to a YouTube video that will desert you. It does indeed take you to github.com/GuyRoyse. So go check out my code, and I'll post that link in the chat as well. And that's pretty much all I've got. Thanks for listening. I went a little long, but are there any questions?
Can we try one more phrase?
Sure.
I can already taste those chocolate-covered hot dogs.
I'm having trouble getting. You pasted that in here, so I'm just going to copy it. Why type when I don't have to?
Not from the movie, it's from the original TV show. So I'm all right.
Was it Shaggy?
Yep.
Well, then it worked. Probably because it had chocolate, hot dog, and taste, which seems like words that Shaggy would say a lot because he was a stoner with the munchies, right?
Yep.
So, cool. So excellent.
Thank you. That was really good.
Thanks. Appreciate it. So yeah, there's a lot of holes in my knowledge, but you know, I can stop my sharing now. As my slides are done. There we go. So
that's the good thing about machine learning, right? You can have holes in your knowledge and it will still figure it all out. So you still got that neural network that can make those deductions for you.
I'm using a neural network to do that right now. Yeah.
That's the best way to
Amazing.
fill those holes in your knowledge is to give a talk.
Yeah, that's very true. Yeah. Yeah, there's an XKCD. I probably should put this in my neural network talks where he says, it sounds way cooler to say that I'm training a neural network to do blah, 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 which is to say I'm raising a child. Well, we are still live on Twitch. So if there's any good questions, so let's go ahead and get them out now. And then if there aren't, I'm going to go ahead and shut down the Twitch stream as I slowly shut down all my running processes.
What's happening next month?
Excellent. So next month we have, let me confirm this. I have it written down. It's out on the website and available. It says I don't have any Firefox. There's my Firefox. So ColumbusJS.org. Next month, we got Rob Richardson. He's doing Vue.js and TypeScript working together like peanut butter and jelly. So we got a Vue.js and TypeScript talk, which I think will be really great. In March, we have Jeff Blankenberg coming. He's going to talk about Alexa. In April, we have Martine Dowden coming, talking about typesetting and CSS. And in May, we have Chris Woodruff. He's going to be doing an Electron talk. And that's everything that's been scheduled so far. If you know anyone that wants to speak, of course, have them message me and I'll be sure to do what it takes to get them on the docket. Like I said, it's been a lot easier to get speakers. I'm scheduled 5 months in advance and I've got several more speakers that I can to add to the list. And Matt actually sent me an abstract just the other day, which I haven't gotten a chance to look at yet. But there's a lot of, I mean, there's plenty of talks to be had. So frankly, there's almost enough that we could go twice a month, except I don't know that I want to run a meetup twice a month. It seems like a lot of work. So yeah. Any other questions? Cool. Okay, well, thanks a lot for attending, everyone. I'm going to go ahead and shut down the Twitch stream, and then we can hang out here and talk until we're all tired of it. Bye, internets.